Okay, so we shall start now. So before we go through the lecture, which is going to be quite lengthy, uh, you have to use this one for the next project, which is going to be the gear pump design. I have a video for that. I'm going to post a video for you. And actually, there's another video about the processes you have to do with the gear pump. Actually, there's, well, I call it this short video show you how to do steps from A to Z for the gear pump. Have you started the project yet? The gear pump design? Anyway, I think you have to start with this week. Just remember something that the part we're talking about is the same one we have in the lab, the pink one. So you have to get the dimensions for the actual shaft. I will bring it to you next week. I'm going to show you what are the dimensions you have to take and include in your report and use it with this calculator. I will send you this one as I told you by tonight. You're going to receive it on email. And that's something else. We're doing that in the advanced manufacturing, which is the machine or the part, and writing the G code for it to machine it on the CNC machine. We'll go back to the lecture, which is going to be about the welding and joining processes. So I told you last week that in the final exam, we're going to have a full section about the welding and joining. So what we're going to cover today is going to be first the fundamental of the welding. First, we're going to have an overview of the welding technology, the weld joints and the physics of the welding, and the features of the fusion welding joints. Also, we're going to talk about the brazing, the soldering, and the adhesive bonding, which are different methods for joining the parts together. Mainly it's going to be permanently as well as we have in the welding. And we're going to talk about the mechanical assembly, which can be divided into a permanent or disassembled types of the assembly processes. So for the joining and the assembly, distinguish is that the joining is welding, the brazing, the soldering, and the adhesive bondings. And this process is going to form a permanent joint between the parts. If I'm going to weld two parts together, they're going to be a new part. It's not going to be an assembly. The assembly process is a mechanical method which usually going to be all the fastening all the parts together, like using bolts and nuts, so we can deassemble the things. Even if we're going to use the rivets, actually you can break the rivets and deassemble the parts later if you need to do that. The welding defined as the joining process in which we are going to have two parts are going to be combined. The combination part is going to be between mating faces or contacting faces by the application of adding the heat or and the pressure or together. The heat alone with no pressure can be applied. I can add the combination of the heat and pressure, and I can do it by the pressure alone with no external heat to be added. The example for the first one is almost all the welding processes. We melt something, we melt the base, and they're going to solidify, making a new part, just heat. The combination of the heat and pressure, if you ever heard about what we call it the spot welding. In the spot welding, we're adding pressure and heat, so we're going to have a small portion of the metal to be melt and joined, of the two parts, sorry. And we're having something called the nuggets. By the pressure alone, you remember the example we saw last time with the explosion welding? We can put the two parts together, have the explosion impact, and it's going to push the parts together, and we have the joining process. In some process of the welding, we may have the filler material to be added to facilitate the merging. And actually, not only in the welding, the brazing and the soldering also having the filling material. Why the welding is important? First is going to provide a permanent joint. Second is going to be the most commercial way to join the parts in terms of the material usage and the fabrication cost. And also is not restricted to the factory environment because you can take the gas bottle, two gas bottles, the oxygen and the acetylene, the torch and the tube, and go outside, do the welding externally. The limitation we have is usually the manual weldings are expensive because the people who are doing the welding, they are experts with the thing. So usually they charge you a lot. Also, is utilize high energy and inherently dangerous because they are sending some gases. Welded parts cannot be deassembled. This is one of the disadvantages, and the quality defects may occur. The fairing surface in the welding are the mating surfaces. We have to put two surfaces together, then we start to weld them. So the part surface in contact or close proximity that are going to be joined is called the fairing surfaces. And the welding usually involves the localized merging of the two surfaces or two mechanical parts at their mating surfaces. The welding usually performed on the parts made of the same metal, so steel to steel, cast iron to cast iron. But in certain cases, we can use dissimilar metals to be joined together. The types of the welding process can be classified into the fusion welding and the solid state welding. And that's what's classified according to the American Welding Society. I advise you that you go through the website of the AWS. And I think you can make a membership with them for free as students. You will learn something from there, and I think they're offering some of the online courses about the welding processes, and this will give you good knowledge for the future. You will use the welding anyway in your life. So the fusion welding is a process of that you're going to melt the base metal. Again, to put two steel plate together, going to join it together. So if the parts are going to be melted and solidified, this will be called the fusion welding. Usually, the filler metal is going to be added to facilitate the process to provide the bulk material. And also in fusion welding operation with no fillers are going to be also called the autogeneous type welding, where only the base metal is going to be melted and solidified. In the solid state welding, we don't have any melting. The pressure alone or the combination of the heated pressures will do the work. So we don't add any extra material, and usually the temperature is going to be below melting points of the metal being welded. No filling material is going to be added in the solid state welding, like what we have in the case of the spot welding. Okay, no added material, the pressure will do the work. So the fusion welding is arc welding. The melting of the metals is going to be accomplished by the electrical arc. We can have the resistant welding type, where the melting is accomplished by the heat from the resistance or the electrical current between the fairing surfaces that held them together under pressure. And we have the oxy-fuel gas welding, where the melting is accomplished by the oxy-fuel gas, such as the acetylene, chemical reaction, the heat can be generating when they have the welding. For the solid state welding, we can have the diffusion type of the welding, and we can have the friction welding, and we can have the ultrasonic welding. Actually, the friction welding and the ultrasonic welding basically can consider the same. The difference is that in friction type, we're going to have the friction due to the rotation of the part, while in the case of the ultrasonic welding, we're going to have the high-speed oscillation to do the friction. The fusion welding is the collisions of is going to be a solid state fusion between the two surfaces held together under pressure at elevated temperature, which is going to be less than the melting point of the base metal. Now, the problem we have with the welding is going to be usually the safety issue. The welding is dangerous to the human worker. So you can see, the first thing you can see that when the people do the welding, they are either putting the shield on their face, or at least they're going to wear glasses. So the heat temperature of the molten metal is dangerous. In the gas welding or the fuse, we're going to have the fire hazard as possible. Many of the welding processes use the electrical power, so the electrical short is a hazard. And we have the ultraviolet radiation. That's why you cannot see directly to the arc welding. And we have the spark, the spatter of the molten metal, the smoke, and the fuse. The fumes are also a hazard on the worker. We can simply do the automation for the welding, like for example, do the machine welding, where we're going to have the welding that's going to be run under supervision of the control of the human operator, but the machine is going to move the torch. We can have the automatic welding. The equipment performs welding without operator control, and we can do the programming for the robotic arm to do the welding. The result is going to be higher productivity, better quality for the welding, and of course, we are going to have high safety because no workers are employed to do the work. Now, this is important about the weld joint because previously we had this question repeated in the final exam. The weld joint is a junction of the edges or the surfaces of the parts that have been joined by welding. And this can be classified into the type of the joints and the types of the weld used to join the pieces that form the joints. So I'm going to show you the both types. First the joints, and second the types of the welds used. These are the types of the joints. Actually, the question was name 5 types of the joints, welding joints. So we have, if I'm going to put them together next to each other with the space in between them, I will call them the butt joint. This one, from the name, is a corner shape, so I'm going to have the corner joint. Overlapping, lap joint. T-shape, T-joints. And this one is an edge joint because actually I'm going to do the welding in the edge between the two parts. So just try to remember the shapes and memorize them. Possibly you're going to have 4 marks for that. Once again, it's butt joint, corner joints, lap joints, T-joints, and the edge joints. The types of the welds we can use to join these types of the joints together is known as the weld type. So the first type we know is the fillet weld. From the name, because it's going to have a fillet shape. You can see it has certain angle. So it can be the inside single fillet corner. We can have the outside single fillet corner joint. We can have the type C, which is the double fillet on the lap joints. And we can have the double fillet on the T joints. Okay, now why we have the dashed line? Because we added the material. At the same time, we melted the original base material, and we have the pool of the liquid, which is going to be solidified, and we're going to end up with the fillet weld. Okay. The other type is called the groove welds. So the difference between this one and the other one is that we need to prepare the material previously, cut it. Okay, so we're going to have a channel, and we're going to fill this channel with the molten metal and the base metal and solidify it. So the types of the groove welds, which require the part edge to be shaped into the groove. We can have it as a square shaped groove welding. We can have it as one single pebble groove weld. We can have it as single V groove shape. We can have it as a U shape, and we can have it as single J shape, and we can have it as double V shape. The spot welding and the seam welding. Now, usually this one is going to be done by adding the pressure and the temperature at the same time, because we cannot access the area where we're going to have the welding joint to be appeared at. So usually the fuse section between the surfaces of the two sheets or the plates is going to be done either in a spot welding, where we're going to have the small spot nuggets, or we can have it as a seam welding. Used for the lap joints, where we don't want to access the edges, and instead we are going to do it inside. And closely associated with resistant welding, where we can run the high current under high pressure in this area. So the high current, because of the resistance of the material, is going to generate very high temperature between the two parts. They start to melt, then solidify. Usually the process is going to be at very short time. Have you ever seen the spot welding in the process of the car manufacturing? It's just a matter of seconds. I can show you a video for that. The same process can be repeated for what we call the seam welding. So instead of having the two spots of the welding, I can run the lap parts between our rollers. Each roller is going to run the current between the parts. As the bar is going to move, we're going to have the seam welding between the two laps. Also, I can have the flange weld and the surfacing weld types. Okay, as you can see here, this will be the flange weld type, and this is the single paste part with the surfacing weld. So this is a single part, but we're still doing the joining on them, mainly to make it stronger. Just imagine that we have a weird part, for example, the crankshaft for the car, and have a certain damage on it. We didn't use it yet. So you don't have to throw this one. You can simply fill it with the welded material and then do the silver finishing for it once again. So you just give it an extra life. And that's what's happened with the high costly material for manufactured. I mean the parts. So usually you overhaul the thing by fix it, by fill it with the welded material, then treat it. Also, we have another type which is called the plug weld and the slot weld. So we're going to make the small hole in the part, in the upper one, then fill it with the welded material. Or I can make it as a slot to increase the contact area between the two parts. This is the plug weld and the slot weld. So what's happening in the welding is, in the case of the fusion welding, achieved to the constants in the welding types, I'm going to have a high density heat energy. So I have to concentrate the heat in a small portion, and that's what we call the heat density. From the terms of the heat density, that means how much power I'm going to add to a small surface area. Higher value, that means I'm going to have higher energy in a small area. So the high density heat energy must be supplied to cause the localized melting of the base metal and the filler in case of I'm going to use it. For some metallurgical reasons, it's desirable to melt the metal with the minimum energy, but it's going to be high heat density. I don't want to increase the temperature to the maximum. I only going to use the energy which is going to be fair enough to melt the metal and do the welding processes. So to make the things focused, I prefer to use a high heat densities, which is going to be calculated by this equation. The power density is power transferred per unit surface area, which is going to be calculated in how much watt per square millimeter I'm going to use. If the power density is going to be too low, the heat is going to be conducted through the work, but never going to melt it. But in case we are going to have too high power density, a localized temperature will vaporize the metal in the affected region. And once again, this will be a bad acting. So there's a practical range for the value of the heat density within which the welding can be performed. Once again, the equation for the power density is the power divided by the area. For the range we are going to have for the power density, for the oxy-fuel, I should stay within the 10 watts per square millimeters. For the arc cutting welding, it's 50 watts per square millimeters. For the resistance is 1,000. For the laser beam is 9,000. And for the electron beam is going to be 10,000. Now, mainly what's happening is for the oxy-fuel, the torch is quite big. So the heat will be distributed over a larger area. In the case of the electron beam, the beam is going to be concentrated through the electromagnetic lens to a very small area in the space because we take the air out. So it's going to get the maximum power density for this type. The heat transfer mechanism in the welding. First, we must know that not all the input energy is going to be used for the melt of the welded metal because simply we're going to have some heat dissipated through the part. So we have to calculate the heat transfer efficiency F1 and the melting efficiency F2. That's what's happening when we do the welding. The structural shape, the microstructural shape of the material is going to look like the following. This part was a melted pool which has been solidified. That's why you can see that the microstructure is going to be a big one. It's going to be usually a columnar grains in the fusion zone welding. Now the area around has been increased to a higher temperature high enough to change the crystal shapes of the material, but not high enough to melt it. So we start to have the coarse grains in what we know as the HAZ, or the heat affected zone. We're going to talk about this one because it was a question in the final exam as well. And the away area is going to have the finer grains because it's not highly affected by the heat. It's got heated, but never reached the recrystallization temperature of the parts. So I think, it has stars. This drawing was given without the definition, and you have to identify that. So just remember, we're going to have the columnar grains in the fusion zone. This is the fusion zone. And this one is the heat affected zone with the coarse grains. And we have the finer grains away from the weld interface. And of course, this is the original cold work grains, which has not been affected by the heat. Now, the heat affected zone, if you ever seen a welded part, that's what you can see around, a burned area. So the definition of the heat affected zone does have 2 stars, is a metal which has experienced a temperature below the melting point, but it was high enough to cause the microstructural changes in the solid metal. You can write it down as you remember it. You don't have to say exactly the same word. You just say that the area which has been exposed to a high temperature, which was enough to change the microstructure, structure, but without melting it. So the chemical composition is going to be the same of the metal. It's the same with the actual metal we have here. I'm sorry. Okay, the same chemical of this metal, not the fusion zone. But this region has been heat treated to a very high temperature, so the properties and structure has been altered to a different properties. The effects of the mechanical properties in the HAZ usually going to be negative. And it is here that welding failure often going to occurs in this area, not in the welding itself. The welding processes we have, in general, we have the arc welding, we have the resistant welding, we have the oxy-fuel gas welding, we have the other fusion type of the welding processes. All these types are involved in the high temperature and the melting of the base metals and the filler if it's going to be used. The other types are the solid state welding, which mainly going to use the pressure and sometimes the heat to a certain temperature, which is not going to cause the melting for the base, but it's going to cause the melting for the filler if we're going to use it. We are going to discuss the welding quality, the weldability of the metals, because not all the metals can be welded, and some design consideration we have in the welding. So just a reminder that the fusion welding is involved in the melting of the base metal and the filler. And the second type is not going to have solid state welding. The heat and or the pressure are going to be used to achieve the welding, but no melting of the base metal occurs, and usually no fillers are going to be added. Now, the first type is the arc welding. What's happening in the arc welding, I think you saw this machine before. Again, to have the arc running a high current, and this will cause the high temperature to achieve. And thus we can add the filler metal sometime to get melt. We say sometimes because sometimes we're only melting the 2 base metal and leave them to cool down. Fusion welding is a process in which the merging of the metals are going to be achieved by the heat from the electrical arc. That's why we call it the arc welding process. The electrical arc simply is going to cause the heat to flow between the electrolyte and the work. Now we can see this one is going to be the negative, this will be a positive, so the current will run all the time and cause the high temperature to occur. The energy from the arc produced temperature is going to be reaching sometimes 5,500 centigrade, which is hot enough to melt any metal. Most of the arc welding processes add a filler metal to increase the volume and the strength of the weld joint. The electrical arc is a discharge electrical current. So we have the positive and negative, so we're going to have discharge between both, and this will cause the high energy to occur because the gap is going to be too small in the circuit. It's sustained by the ionized column of the gas or the plasma, which is the heated gas, when we're going to do the work. The arc welding electrolytes can be consumable type, which melting to do the process, or can be non-consumable type. In this case, we add the filler metals. So in the consumable types, the arc itself is going to consume during the process of the welding, and the source of the filler metal is going to be in the arc welding process. So what everybody knows is what we call the welding rods. Is the rods which are covered with the flux material, and when we do the contact, it starts to melt and consume. It's getting shorter, and so again to remove it, we'll change it with another one. So the welding rods, it's the most common things, which are 9 to 18 inches length and 3/8 inches or less in diameter, and must be changed frequently. And also, instead of using the rods, we can supply a wire. So the wire is going to be supplied all the time from the spool until we're going to do the process of the welding. So the spool, which is going to be the roller, is going to keep feeding through the handle itself to do the process of the welding. The non-consumable type, we're going to have a type which is not going to be melted during the process, and usually is made of the tungsten, which is going to have very high melting temperatures. But still is gradually depilated during the welding process, and any filler metal must be supplied by the separate wire fed into the weld pool. The arc shielding process. This is a very common question, and the most common answer is wrong. Now, when we say the arc shielding, we don't mean the goggle we're wearing and nor the shield we're putting on our face. Now, have you used the laser cutter upstairs? You hadn't used it? Now, almost all the processes which involving the high temperatures, like the plasma cutter, the laser cutter, and the welding, usually the high temperature will cause the oxidization of the material. Thus, we have to use, for example, a gas, usually it's going to be CO2, because it's the easiest one to get, to make a shield over the molten metal, and thus we are going to prevent the oxidization of this metal. And that's what we call the arc shielding. At high temperature, in the arc welding, the metals are going to be chemically reactive to the oxygen, nitrogen, and the hydrogen in the air. So the best thing to protect them, are going to put a shield around it. This can be done by either using the shielding gases or the flux. The shielding gases can be the argon, can be the helium, and can be the CO2, and the flux. Have you done the soldering yet? Have you seen the white powder you put the soldering material in before you do the soldering? This is a flux material. I'm going to show you some example for that. So just remember that the arc shielding is protect the operation by adding the, by making isolating from the air with either using the shielding gases or the flux material. So the flux is a substance that prevents the formation of the oxidized or other contaminants in the welding, or dissolves them and facilitates the removal. So usually when you do the welding, with the arc welding, with the rod, usually you have to clean it later, again, to remove something like the slug. This slug is the flux material. It's going to be melt first, then solidify. It's not going to be a part of the welding process. You have to clean it. Usually they hammer it a little bit and they remove this slug. So once again, the flux is substances that prevent the formation of the oxides and the other contaminants in the welding process, or dissolve them within the facility and facilitates the removal. This will provide the protective of the atmosphere for the welding and stabilize the arcs and reduce the spattering of the sparks. We have various types of the flux application methods. We can simply bore it as a granular flux during the operation. We have it as a powder, we pour it and do the welding process. We can do it as the coat around the stick. And we can have it as a tabular electrodes, which the flux is going to be contained within the core instead of from the outside. And this is the most common one. This is the sticks or the filler, and this is the flux built up over it. The other type can be a cylindrical shape, something like the spaghetti one, and the filler, the flux is going to be inside instead of the outside. In the case of the gases, we send the gases through the operation. Usually it's going to be within the handle. We send the gases like the helium or the CO2 from the sides, thus it's going to make a foam, gas shield to prevent the oxidation process. The types of the consumable electrolyte arc welding process are: first, the shielded metal arc welding, the gas metal arc welding, the flux cored arc welding, the electrode gas welding, and the submerged arc welding. So we're going to have 3 lines about each process in our way. The first one is the shielded metal arc welding. The same stick we saw earlier is going to be used. Once again, we're going to run the current. We're going to have a small gap. Usually, when you do this process, you're going to try it later anyway. When you do this process, you have to mind the gap. You are going to, usually the professional people can handle very nicely. If they are going to have direct contact, no welding will happen. It will stuck on the machine. So the shield metal arc welding process is usually consumable electrode consisting of the filler metals coated with the chemical that provide the flux and the shielding. We know it as the stick welding. This advantage of the stick welding is that the stick must be periodically changed from time to time. Highly current level may melt the coating permanently. The application is used for the steel, stainless steel, cast iron, and the certain non-ferrous alloys, but never used for the aluminum and alloys or the copper alloys and the titanium. So instead of that, we can go to the gas metal arc welding on what we know as the MIG. Now in the MIGs, you can see that it's not going to be coated. The filling material is going to be bare, but instead of that, we are going to send the gas to do the shielding. So once again, the gas metal arc welding is using the consumable bare metal wire as the electrode and the shielding by the floating of the arc within the gas. The wire is going to be fed continuously from the spool. Okay, so actually when you press the gun switch, the pull roller will start to move, and then it's going to continue feeding the gun with the electrode material. The shield gas, as we mentioned earlier, can be argon or helium for the aluminum case and CO2 for the steel welding. The bare electrode wire plus the shielding gases will eliminate the slag weld bed, and then no need for the grinding later to remove the slag. So it's better arc time because we don't have to change the filler ourselves. Better use of the electrode filler metal because simply usually the end of the stick cannot be used, but in this one we're going to have continuous feeding. Higher deposition rates and eliminate the problem of the slag removal and can readily be automated by fixing the handle on the robotic arm. The flux code is similar to the arc code, but the thing is that the material, the flux core, is going to be inside, not at the outside. Actually, this is the MIG type. I should put this photo on the other side. So as we said, we are going to feed the electrode through the gun, and that's what's happened. That's the electrode. And the gas is coming from here to make the shield. I should change this picture location. So in the case of the flux core arc welding, we are going to have the adoption of the shielded metal arc welding to overcome the limitation of the stick electrodes. So we're going to have 2 versions, either the self-shielded material, where the core is going to be included in the components that produce the shielding gases, or we can use the gas shielded type. The electrode is going to be continuous consumable tubing, and usually it's going to be come in coils, because now when we coil the things, the flux is inside, so it's not going to break up. The presence or the absence of the external supply shielding gas distinguished by the self-shielded or the gas-shielded type. Now, this method is called the electrode gas welding. It's not much difference from the other methods, which using actually an electrode, which is going to be melt due to the electricity. But in this case, we're going to have something called the welding mold or shoe. This is a cross section of the work. So actually we're melting the filler, and it's going to start to solidify at the base and upward. This shoe is going to be on this direction and the other side, as we can see here. So it's going to fill the gap between the two metals, solidify. To increase the solidification, we're usually running the water through the something like the heat exchanger. The shoe actually is heat exchanger. So this will, the water is going to absorb the heat from the molten metal and make it solidify at a faster rate. So the electrode gas welding process is using the continuous consumable electrodes, which is going to be a flux cored wire or the bare wire with externally supplied shielding gases, and the molding shoe to contain the molten metal. So it's something like actually we're doing the casting process, but it's going to be instantaneous because the materials just keep melting and added all the time. When the if I'm going to use the flux cored electrode wire, no external gases are going to be supplied, and if I'm going to use the bare type wire, I have to add the gases to prevent the oxidization. The other type is called the submerged arc welding. So you can see that we're adding the flux and do the welding at the same time, and thus we are going to remove the slug when we finish the welding process. So in the case of the submerged arc welding process, we are going to use a continuous consumable bare wire electrode with the arc shelled by cover of a granule flux. The electrode wire is going to be fed automatically from the coil. The flux is going to be introduced to the joint slightly ahead of the arc by the gravity from the hooper, as you can see here. So this is my consumable electrode is going to move in this direction, and the material is going to be added ahead. So what's happening, that's going to be melted, solidified, and we have to remove it later. The other type is non-consumable type. Now, usually the first one we saw here was called the TIG, the other one is called the MIG. So the non-consumable type of the electrode, mainly we are going to use the external types of the material to be fed in. The classified as the gas tungsten arc welding, the plasma arc welding, the carbon arc welding, and the stud welding. So for the gas tungsten arc welding or the TIG, the other one was the MIG, and this one is the TIG, is going to use a non-consumable tungsten electrode, this one in the middle. And this will generate a high temperature heat. So it's either going to melt the base metals, which is going to be solidified to make one part, or we can add the external material. The usually non-consumable tungsten electrode and the inner gas for the arc shielding, the temperature can be, the temperature for the tungsten itself is 3,410, and for the tungsten inner gas welding in Europe is called the WIG, we call it the TIG in Australia and United States. It can be used with or without filler material, and if I'm going to use the filler material, then it's going to be added to the weld pool from the separated rod or wire externally. It's not going to be fed like what we had in the consumable types. The application usually is going to be for the aluminum and the stainless steel. The advantage is we are going to get a high quality of the welds for suitable application. No spatter because we don't have a filler metal through the arc itself. And also have little or no post-weld cleaning because of no flux present. We're usually using the gas. Yes? Oh, sorry. I thought you were asking a question. Disadvantage is generally going to be slower and more costly than the consumable electrode arc welding processes. Now, this is a process called the plasma arc welding. We talked about the plasma and the advanced manufacturing technologies. Now, the plasma is once again is a gas. Is going to be energized and heated by using the tungsten electrolyte. So this is plasma gas, and we have the shielding gas. So we have the primary and the secondary gases. This one is going to make the shielding to prevent the oxidation, and this one is going to accelerate the air and make the plasma arc. So a special form of the GWA which is going to be constructed as a plasma arc, which is going to be directed at the weld area. The tungsten electrode is going to be contained in the nozzle, as you can see here. And this will focus the high velocity stream of the inner gas, which mainly is going to be argon, into the arc region from the high velocity intensity of the whole plasma arc stream. Temperature can be reached 28,000 centigrade. So producing the plasma jet of the small diameter and very high energy can give you a very high density. The advantage is going to be first, good arc stability and the excellent weld quality, better penetration control than the other arc welding processes, high travel speed, can be used for the weld of almost any metals. But the disadvantage is going to be usually the high equipment cost and the large torch size than the other types of the arc welding. But it's very common to use this one in the automation process. We can put it on CNC machine to do the both cut and welding. The resisting welding, which is the base of the spot welding process. So as you can see here, we're going to have the cathode and the anode, pressurize the area and run the high current, cause the melting to occur, and we're going to have what we call the nugget. So the resistant welding is a group of fusion welding processes. Use a combination of heat and pressure to accomplish the collisions. I think this is possibly a question as well. That's why I highlighted the things. So usually the heat is going to be generated by the electrical resistance to the current flow at the junction to be welded. The resistant welding showing the components in the spot welding, which is the main process in the resistant welding group. So once again, we can make it as the resistant spot welding, just a spot between the two plates, or I can make it as what we call it the line welding or the seam welding. So these are the two poles, the positive and negative. I pressurize the two plates together, and we're going to have a seam and instead or line instead of the spot. Also, I can have it as the resistant projection welding type. So I'm going to do the pressure, and instead of having the biggest area, the edges should be provided as a small parts. So the current will be running between these two parts and melted and joints. And also I can use it in this case as what we do in the, or this case as we do in the case of the wire mesh processing. The oxy-fuel gas welding was using the oxygen with the other gas, chemical reaction, generate a very high temperature, and mainly is going to be used with the filler material. So it's a group of fusion welding operation that burns the various of the fuel mix with the oxygen. The oxyacetylene welding methods is the fusion welding performed by the high temperature flame of the combustion of the acetylene and the oxygen. The flame is going to be directed by the welding torch. The filler metal is sometimes to be added. The composition must be similar to the base metal. And the filler rod usually going to coat it with the flux to clean the surfaces and prevent the oxidation. The oxyacetylene torch shape is going to have the three different levels: the inner cone, the acetylene feeder, and the outer envelope. The temperature usually inside is going to be the highest, because what we have is the oxygen mainly is going to be the higher composition, where we're going to have the temperature of 3,480. The acetylene feeder is going to be the orange color. This is the blue, this is orange color. which is the S2019 feeder, and we're going to have the outer envelope of 1260, which is going to be enough to do the process of the welding. The alternative gases we can use instead of the acetylene can be the methylene propylene, the hydrogen, the propylene, the propane, and natural gas. Other fusion welding we can have, which the other processes can not be classified as in arc, resistance, or the oxy-fuel welding, which use a unique technology to develop the heat of the welding, for melting, and the application are typically going to be unique. For example, we can have something for the nanotechnology, nanomachining, very small parts. That's include the electron beam welding. We are going to send the electron beam to a very small area to have a very high power density, which causes the melting process. I can use the laser beam welding instead of the cutting. I can use the electroslag welding, and I can use the thermal welding. I think that you saw a video for both of these two. The electron beam welding, what did we say about the electron beam cutting process? What do we need? A vacuum chamber. Okay, so if we need a vacuum chamber, that means there's no air, so actually there's no oxidization, so we don't need a flux for this process. That's the electron beam welding process. A fusion welding process, which the heat for the welding is going to be provided by the highly focused, high intensity stream of the electrons, which is going to be striking the work surface. So that's what we are going to have. We are going to have the high voltage, we are going to have the bioscope, primary anode, the electron beam. I'm going to use the electromagnetic focusing coil, or what we call the electromagnetic lens, which is going to be concentrate the beam in a small area. All to be done within the vacuum. Thus, there is no oxidation to appear. The heat is going to be concentrated on a small area, cause the melting to occur. So, electron beam gun operates at the high voltage of 10 to 150 kilovolt typical to X-ray the electrons. The beam current are going to be usually low, and the power is not going to be exceptional, but the power density is going to be very high. We need the vacuum chamber. So when first developed the electrical beam welding have to be carried out of the vacuum chamber to minimize the distribution of the electron beam by the air molecules. And the pump down time can be taken as long as 1 hour. But now they modify the things to have 3 vacuum levels in the electrical beam welding. This can be either the high vacuum welding, we can have the medium vacuum welding, or we have non-vacuum welding processes. The advantage and disadvantage of the electrical beam welding is the advantage are the high quality of the welds, deep and narrow profile, because it's concentrate the electron in very small area. We said it's have the highest power density. Limited heat effective zone, so low thermal distortion will happen. No flux or the shielding gas is needed because we're doing that in the vacuum. Disadvantage are the high equipment cost, the precious joint preparation and the alignment required, and the vacuum chamber is usually required, and some safety concern because the electronic beam welding is going to generate the X-ray. We can simply use the laser beam, which melting the parts during the cutting to do the welding process. So the laser beam welding is a fusion welding process in which the collision is going to be achieved by the energy of the highly concentrated coherent light beam focused on the joint. Usually it's going to be performed with the shielding gases because now we're working in the air. And this to prevent the oxidization. Usually the film metal not usually added, and the high power density in small area is going to be achieved. So the laser beam welding often used for the small parts. No vacuum chamber is going to be required. No X-ray emitted at the laser beam welding. Laser beam can be focused at direct by the optical lenses and the mirror instead of the electromagnetic lenses. But the problem is not capable of the deep weld as the high in depth width ratio, like what we had in the problem in the case of the laser cutters, cannot cut more than 1 centimeters. So the maximum depth we can have can be 19 millimeters if we're going to have a big machine. The thermal welding, well, this one is mixing between the casting and the welding. So what's happening in the thermal welding is the heat is going to be produced by the superheated molten metal from the chemical reaction of the thermal material. But the thermal is a mixture of the aluminum and the iron oxidized fine powders that produce the exothermic reaction when going to be ignited. It's also used for the industry bombs and the film metals obtained from the liquid metal, and the process used for the joining, but has more common with the casting than the welding process. So we put the thermal material, we ignite it, it's going to start to melt, fill the cavity between the, for example, this is the railway beam, and it's going to solidify. And it's going to require an extra machining process when we finish. Now, the other type is the solid state welding. No melting will occur in this process. And this can be achieved either by adding the pressure or adding the heat and the pressure, but usually the heat is not going to be high enough to melt the work surface. For some of the solid state welding processes, the time is going to be also a factor. No film metal is going to be added in all the cases. And each type of the solid state welding process has its own way of the coating or the creating the bond at the fairing surfaces. If no melting occurs, then no heat affected zone will be generated. So the metal around the joints retain at the original properties. Many of these processes produce a weld joints that's going to be bond entire contact interface between the two parts rather than a distinct spot or seam. And some of these processes can be used to bond the dissimilar materials without concern about the relative melting points, the thermal expansion, and other problems that arises in the fusion welding. Now, the first one is the eldest method, which is the forge welding. Also, we can do the cold welding, the roll welding, the hot pressure welding, the diffusion welding, the explosion welding, the friction welding, and the ultrasonic welding. So for the forge welding, simply we putting the two parts together and start to hammer them. So by just adding the pressure is going to be one part. And this one of the oldest method of the welding processes. So forge welding is welding in which the components are going to be joined are heated first to a hot working temperature range. Then it's going to be forged together by the hammering or the similar means. It's very old methods which date up to 1000 BC. One of the minor commercial important today except for its variants. The cold welding process just compress the part against each other at very high pressure. It's going to be performed at room temperature. So usually you need to do the cleaning for the parts by simply degrazing the wire, brushing, and immediately before the joining. No heat is going to be applied, but the formation raises at the work temperature. And at least one of the metals, preferably or both, must be a very ductile material. Ductile, so it can go through the other one. Usually we can use the soft aluminum and the copper suited for the cold welding process. The application usually is going to be in the case of using the electrical connection between the wires. For the roll welding, the same process, but in this case we're going to run them between two rollers. So it's a solid state welding process in which the pressure is going to be sufficient to cause the collisions and applied by the means of the rollers, either with or without external heat. It's a variation of either the forge welding or the cold welding, depending on whether the heating of the work part is going to be done prior to the process. If no external heat is going to be done, we call it the cold roll welding. If I'm going to add the heat, we call it the hot roll welding. The diffusion welding. Now, these are my samples. I'm going to once again pressurize them together but at the same time, again, to heat up the chamber. So once again, I added the pressure and heat in this case. So usually it's going to be controlled in controlled atmosphere to keep it at the constant temperature with sufficient time for diffusion and collisions to be occur. Usually the temperature within the chamber is going to be less than half of the melting temperature. The plastic deformation at the surface is going to be minimum, and the primary collisions of the mechanism in the solid state diffusion, and the limitation we have for this process is going to be some time required for the diffusion can range from seconds to hours. We saw the explosion welding. We said we are going to put the explosive on the top of the layers. By exploding that, we are going to have the high impact, which welding the parts together. So the rapid coincidence of the two metallic surfaces is going to be caused by the energy of the detonated explosive. No filler material is used, no external heat applied, no diffusion occurs where the time is going to be too short, and the bonding meteorological combines with the mechanical interlocking process is result from the rapid or the wavy interface between the two metals. Usually it's used for the two dissimilar metals, for example, to clad of one metals on the top of the base metal over the large areas. I think you saw this one before, the friction welding. So the part will rotate, contact with the fixed one, the friction, done is one part now. So the friction welding is solid state process in which the coldness is achieved by the fractional heat combined with the pressure. When properly carried out, we're not going to have any melting at the fairing surfaces. No filler metal is going to be used, no flux, no shield gas is normally used. This can be used to join dissimilar metals as well, and widely used commercial process where they're amenable to automation and the mass production. The process also can be used in another method, which is called friction stir welding. So these are two different surfaces, material, and the friction is going to join them together. So what's happening that this device is going to bring the two materials to each other by the friction process and make them as one part. So the friction stir welding, we're going to have rotating tool is going to be fed along the joint line between the two work pieces, and during the friction heat and mechanically stirring the metals from the weld seam. So the difference between the friction stir welding than the friction welding is the heat is going to be generated by the separate wear resistant tool rather than the parts themselves. The application is the bolt joints in the large aluminum parts in the aerospace, automotive, and the shipbuilding processes. Now, this is the last style, which is the ultrasonic welding. In the ultrasonic, we're going to have very high oscillating between the parts, and this will cause the friction to occur, and then the parts are going to be joined together. So what's happening is that we're going to have the two components going to be held together at the beginning under higher pressure, and we're going to have the oscillating shear stresses of the ultrasonic frequency are going to be applied to the interface to cause the collisions. The oscillating motion breaks down any of the surface's films to allow the in-time contact and the strong meteorological bonding between the surfaces. Temperature usually is going to be below the melting temperature. No filler, no fluxes, no shield gases, and generally limited to the lap joints on the soft material. Usually in the weld quality, we have to consider with the obtaining the acceptable weld joints, which is going to be strong and absent of the defects. Now, the welding is one of the most manufacturing processes which is going to contain defects. So it's also concerned, the weld quality concerned with the method of the inspecting and the testing of the joints to assure the quality. So what we're going to cover as a topic in the weld quality is going to be first the residual stresses and distortions, the welding defects, and the inspection and the testing method we have for the weld quality. So one of the most common problem we have in the welding is the residual stresses and distortion. Now, these are the two parts. We're going to melt them. they were at room temperature. It's going to increase the temperature, then it's going to cool down. That's what will happen. The distortion. Cool down, so it starts to bend. So the rapid heating and the cooling in localized region during the fusion welding result in thermal expansion and contraction that cause residual stresses to occur. And these stresses in turn cause the distortion or the ravage of the parts. The situation in the welding is going to be complicated because simply we're going to have a heating very localized in the area. The melting of the base metal is going to be in these regions, and the location of the heating and melting in this motion are going to occur. To minimize the warpage, we can do the following. First, we can fix the two parts before we do the welding. So when they're going to be heated and cooled down, not going to be ravaged. Also, we can preheat it, increase the temperature before we start to do the welding process. The welding possible defects are, first, we can have the crack within the welding area. We can have some cavities where the air bulb is going to be within. We can have some solid inclusions, dirts, or even the flux. We can have imperfect shape or unacceptable contour. We can have incomplete fusion, and some other miscellaneous defects may occur. So first, the welding cracks. These are the cracks we may have either on the work or on the welding area. So the welding cracks is a fracture type interruptions either in the weld or the base metal adjacent to the weld area. Both are going to increase the temperature, then it's going to be contract, and that's why we have the fracture within. Serious defect because it's going to be discontinuity in the metal that this significantly is going to reduce its strength. And it's caused by the impediments or the low ductility of the weld or on the base metal combined with the high restraint during the contraction type. In general, these defects must be repaired. Usually you remove the welding and start to redo it once again. The cavities, we have two types. Either we're going to have some porities where we're going to have some voids within the weld material because some of the gases interrupted during the solidification process. Or we can have the shrink void, where the cavity formed by the shrinking during the solidification process. It's getting smaller and leave some cavities. We also can have some solid inclusions, where non-metallic material is going to be interacted with the weld metal. And usually this one is coming from the slug we have for the flux material. Most common slug inclusion generated during the process is going to be from the one using the flux. Usually the cavity is going to be generated mostly when we're using the gas. Okay, so each one have advantage and disadvantage at the same time. Incomplete diffusion, this is a very common mistake, especially for the people who are doing the welding for the first time. What's happening is that the weld bed in which diffusion is not going to be occur through the entire cross section of the joint. So we're going to have some discontinuities or incomplete diffusion. The weld profile in the arc welding are. Okay, now this one have 3 stars. This is the desired shape, the good profile. Sometimes we may have the undercut, extra melted area, and thus we are going to have weakness here. So portion of the base has been melted away, which not meant to be. Sometimes we didn't add the material, the filling material at a constant speed, and thus we're going to have underfill for the metal. So we're going to the pressure in the weld below the adjacent base metal surface, and the last type is going to be the overlap. Now in this case, we're going to add an excess material, so it's going to be spilled beyond the joints onto the part, but no fusion will occur. So to inspect the welding quality, we can either do that by division. Take a look to the part. The expert people will say, okay, now these are the defects. We have to change it. Also, we can do it through the non-destructive evolution. So we are not going to break the joint to see it. Simply, we can inspect it with either using the ultrasonic testing or the X-ray or we can use the dye penetrating and the fluorescent penetrating test, or we can use the magnetic particle testing. Or the other case is we have to break it, either by using the mechanical test or the metrological test, by simply break it and check the defects of the surface. Now, not all the metals can be simply welded, and we can do another two methods, which is going to be the brazing, the soldering, or simply just using the adhesive bonding, like the glue. Now, we said that the adhesive bonding is a thermoset material, which can be simply liquid. Under the heat is going to be solidified. So we're going to cover the brazing and the soldering, which mainly the same process, but with small differences. So the brazing and the soldering, both using the filler metals to permanently join the metal parts, but there is no melting of base metal. So unlike the other processes, we're only melting the filling material, but not melting the base itself. So if you have done soldering upstairs, when you do that for the electrical circuit and the components, like the resistance or whatever the thing is, the base metal is the resistance. So you don't melt the resistance, you're only melting the soldering filler. Use the brazing or the soldering or the fusion welding if we are going to have the metal with poor weldability. If we are going to have two dissimilar metals are going to be joined. And also, if we are going to have the intensity of the heat of the welding may damage the component. You're not going to use the welding for the electrical circuit. The geometry of the joint is not suitable for the welding. I'm going to show you that. Now, have you seen the pipes when you weld the pipes together? The copper pipes for the water? So you're hardly putting the pipes inside the joint, but you still can fill the material inside these small gaps. Because what we're going to have is the capillary action, where the molten filler is going to fill all the cavity by the capillary action. You know the capillary action? Where the clamping of the liquid on the wall of the solid. And when we're going to have high strength, it's not going to be required, like the joining of the steel, for example. In the case of the adhesive bonding, we use the forces attachment between the filler material and the two closely spaced surfaces to bond the parts. The filler material is going to be adhesive bonding, which is non-metallic. It's actually plastic. And the joining process can be carried out at the room temperature, or sometimes just try to increase temperature to increase the rate of the solidification. That's the brazing process. Cover pipes. So what's happening is, as joining a process in which the filler metal, just the filler, is going to be melted and distributed by the capillary action between the faying surfaces of the metal parts being joints. So once again, what we can see here is hardly sensed gap between both the joint and the pipe. But the molten metal will be simply filling all the cavity in between. So no melting of the base metal occurs. Only the filler will be melted. The filler metal is going to be melting temperature is going to be greater than 450 degrees. But it's going to be less than the melting temperature of the base metal to be joined. For example, I'm going to use the filler material, which is going to be melting at 650 degrees to melt the copper, for example, which is going to have a melting temperature of 750 degrees. So the base is not going to be melted, but the filler is going to get melted. Now, once again, just remember that the melting temperature of the filler is greater than 450 degrees in the brazing. If the joint is going to be properly designed and the brazing operation is properly performed, the solidification joint will be stronger than the filler metal out of which it was formed. Any metals can be joined in the brazing, including the dissimilar materials, and can be performed quickly and consistently, permitting the higher production rate. We can simply do the multiple joints like that. Multiple joints can be simply brazed at the same time. Less heat and power required than the fusion welding because the melting temperature is lower. The problem with the heat affected zone in the base metal is going to be reduced but not eliminated. And the joint areas that are going to be inaccessible by the many of the welding processes can be brazed simply with the brazing process because of the capillary effect. Still, we have disadvantage and limitation for the brazing process are. First, the joint strength is going to be less than the welding joints. The joint strength is going to be likely be less than the strength of the base metal. The high surface temperature may weaken the brazed joint. For example, I'm going to use a pipe at the temperature of 600 degrees for the water inside, not water, the oil, for example, is going to melt the filler material, and then we're going to destroy the joint. The color of the brazing metal may not match the color of the base metal parts if this is going to be an important. The application we have for the brazing are the automotive, we're joining the tubes and the pipes, the electrical equipments, the cutting tools, the jewelry, the chemical process industries, the plumbing and the heating contractors join the metal pipes tubes by the brazing and repaired on the maintenance work. The brazed possible joints are, now you can see that we're not going to put the structure at the top, like the joint at the top, like what we had in the case of the welding. Now, the material will fill the cavity. We're going to have the brazed joint in the cavity. So you can have a differentiate, which is impossible to be done in the case of the welding process. So we have the first brazed joints going to be the butt and the lap joint. Okay, so geometry of the butt joints are going to be usually adopted for the brazing. The lap joints are going to be more widely used since they're going to provide a larger surface area or interface area between the parts. The film metal in the brazed lap joints is going to be bonded by the base part through the entire surface area rather than the only at the edges as what we had in the case of the welding process. The metal desirable for the brazing are, first, we should have the melting temperature of the filler metal is going to be compatible with the base metal. We don't want to have the filler metal melting temperature higher than the base metal melting temperature. Low surface tension in the liquid phase for the good wettability are desired. The high fluidity for the penetration into the interface. Capable of being brazed into a joint of adequate strength for the application, and finally avoid the chemical and the physical interaction with the base metal. Some of the popular film materials we have for the brazing are, first, for the aluminum, we can use the aluminum and the silicon. For the nickel copper alloy, we can use the copper. In the case of the copper, we're using the copper and the phosphorus. The mixing of both is going to have a melting temperature less than the copper itself. For the steel and the cast iron, we can use the copper and the zinc. And for the stainless steel, we can have the gold and the silver. Now, what's happened is that, have you noticed that most of the car radiators are made of the aluminum rather than the copper? And the older they used to make them out of the copper. What's happened is that actually the heat transfer through the copper is better than the aluminum. But the material we're using for the brazing, when we add the phosphor, is going to reduce this process, less conductivity, and thus is going to make it worse. But in the case of the aluminum, we're using the aluminum itself. So all the structure is going to have a good heat transfer. So how we can apply the filler metal? Simply by using the filler rod, and this is the most common one. Filler rod, heated, is going to melt, fill the clearance, and solidify. Sometimes, if I'm going to have complicated shapes like that, we are going to put the ring, especially if it's going to be cylindrical shape, we add the ring or the filler metal, we heat it up, it's going to be melt and fill the clearance cavity. The fluxes we can use for the brazing, now once again, because we're going to have high temperature, we're going to have the danger of the oxidization, so we need to use the fluxes. Similar purposes as what you had in the welding, they dissolve, combine with, and otherwise going to be inhibit formation of the oxidized and other unwanted byproducts in the brazing processes. To have a good flux in the brazing, we should have low melting temperature for the flux, low viscosity so it can be displaced by the filler metal, facilitates wetting process, and protects the joints until solidification of the filler metals occur. The heating method for the brazing, mainly we are going to use the torch brazing. The torch will melt the filler and we're going to have the brazing process. Sometimes we can use the furnace brazing, especially if we're going to use this process, the ring of the filler metal. Put that in the furnace, the filler will melt, continue melting and filling the cavity of the clearance. And we can use the induction brazing using the electrical resistance to make the induction heat. We can use the resistance brazing by heating by electrical resistance on the pot. We can do the double brazing where the molten salt or the molten metal pad, we are going to put the material in and take it out. It's going to fill everything. And we can have the infrared brazing, which is the high intensity infrared lamp. Now, the soldering is exactly as the brazing, but with one difference, that the melting temperature of the filler metal is going to be less than 450 degrees. So if you are going to be asked what the difference between the brazing and the soldering, it's all about the melting temperature of the filler material. Brazing is more than 400 degrees, and in the case of the soldering is less than 450 degrees. Once again, we're going to have the capillary action between the fairing surfaces of the metal parts being joints. No melting of the base metal, but the filler metal will get to wets and combines with the base metal to form the metallurgical bond. The filler metal, usually called the solder, and the closely associated with the electrical assembly. The advantage, we're going to have lower energy to be used than the brazing or the fusion welding because of the lower melting temperature. We can have variety of the heating method available, good electrical and thermal conductivity in the joints, and easy repair and rework because we can melt it and take it out and do the soldering process once again. But the disadvantage is usually the low strength unless reinforced mechanically. And also the joints going to weaken or melt at elevated temperatures. And this is very common problem we have in the electrical circuits which working at very high current, because what's happening, the high temperature will melt the soldering points. The solders, which traditionally alloys of the tin and the lead, which both have very low melting temperature. The lead problem is going to be a poisonous material and the percentage is going to be minimized in most of the solders. For the tin is chemically active soldering temperature and promotes the wetting action for the successful joining. In the case of the soldering of the copper and the tin for the intermetallic compounds that strengthen the bond, and the silver and antimony is going to be used for the soldering alloys. The function of the soldering fluxes once again is going to be the same thing exactly. So is going to do the molten of the soldering temperature, remove the oxidized film and tarnish from the base part surface, prevent the oxidization during the heating, promote the wetting of the fairing surfaces, and be readily displaced by the molten solder during the process, and leave the reside in the non-corrosive and non-conductive material. Now, this is a mechanical joint. If I would like to increase the strength, instead of doing as the ordinary method, simply just bend the wire, and this will increase the strength of the joint. So this is the crimped lead wire on the PC board, and this is the plated through hole of the PC board to increase the solder contact surface. Also, I can use the hooked wire type, or I can use the twisted wire type. The soldering methods can be done by hand, and this is the most common one. It can be done by the wave soldering, and we can do by the reflow soldering. Now, this is the wave type. I simply going to spray the joints with the molten solder, and it's going to be solidified. And this is very common use in the case of manufacturing the big electrical boats. Now, the last method we have is the adhesive bonding, where the joining process in which the filler material is going to be used to hold the two or more closely spaced parts together by having the surface attachment. It's used a wide range of the bonding and the sealing application for the joining of the similar and dissimilar materials such as the metals, the plastic, the ceramic, the wood, the paper, and the cardboard. And it's considered as a growth area because of the opportunities for the increased applications. Now, for example, back in my time when I was a kid, we didn't have the super glue. Now it's became a very popular thing in the manufacturing. So the adhesive is going to be the film material. Usually it's going to be non-metallic, and usually it's polymer, which is, once again, is thermoset polymer. The adherent is the part being joined. So the adhesive is the film material, and the adherent is the part to be joined. The structural adhesive is capable of forming the strong, permanent joints between the strong, rigid adherents. The advantage we have for the adhesive bonding is applicable to a wide variety of the materials. Bonding occurs over the entire surface area of the joint because we can fill the whole area, full area with the bonding material before we're going to join them. Low temperature curing avoids the damage to the parts being joined and can be used for the sealing as well as the bonding, and simply can be, the joint design is going to be often simplified. For example, we can have just two flat surfaces can be joined without providing a special part features such as the screw holes. The limitation we have that the joints are not going to be as strong as the joining methods. The adhesive must be compatible with the material being joined, and the surface temperature are going to be limited, and the cleanness and the surface preparation prior to the application of the adhesive is very important. And we have some curing time can limit the protection rate, and we need to do the inspection of the bonded joints, but it's going to be usually difficult. So how we cure the adhesive bonding? Just leave it as a matter of time. So the process by which the physical properties of the adhesive are going to be changed from the liquid to the solid, usually by the chemical reaction to accomplish the surface attachment of the part, is called the curing process. The curing often aided by the heat and or some catalyst because it's chemical reaction. Usually the curing takes time, and this disadvantages the production. Now they can tell you that the joining time, the curing time for most of the glue you have can be taken up to 1 week. Usually it's going to tell you 24 hours. So you have to keep it contact with each other for this time until they're going to be get the cure. The pressure is sometimes going to be applied between the part to activate the bonding process. The joint strength usually going to depend on the strength of the adhesive and the attachment between the adhesive and the adherent. The attachment mechanism can be simply done by the chemical bonding, and it can be done with the physical interaction, and we can do it with the mechanical interlocking. So in the case of the mechanical interlocking is the roughness of the adherent causes the adhesive to become intelligent and the surface asperities, simply because we're going to have more cavities, thus we're going to have more adhesive material. The joint design, the adhesive joints are not as strong as the welded, brazed, or the soldered joints, so the contact area should be maximized as much as possible. So that's why we do the roughness. The adhesive joint is going to be stronger in the case of the shear and the tension loads, but the weakest is going to be in the cleavage building. So this is bad. We cannot make it as a cleavage force, but it's going to be very good in the case of the shear and the tension process. The adhesive type can be simply a natural adhesive. We can have the inorganic adhesives, and we can have the synthetic adhesives. The application method, simply we can add the adhesive by using the manual brush and the rolling. We can use the silk screening. We can use the flowing using the manually operated dispensers, and we can do it by spraying, and we can do it by the automatic applicators, and we can do it by the roll coating. So for the adhesive bonding to succeed, the part surface must be extremely clean before you add the adhesive on the surface. Now, the last thing for today's lecture is going to be the mechanical assembly, and I think that you know about that. The first thing is going to be the threaded fasteners, also the rivet and the eyelets, an assembly method based on the interface fits, and some other mechanical fastening methods. So the difference between all the other processes we covered earlier, the welding, the adhesive, the brazing, and the soldering, is going to be a permanent joining. The mechanical assembly is using the various of fastening methods to mechanically attach two or more parts together. In most cases, the discrete hardware components called the fasteners are going to be added to the parts during the assembly process. That's how we can hold it. But we still have another methods we can join the parts together. In other cases where the fastening involved in the shaping or reshaping of the components and no separate fasteners are going to be required. The major classes of the mechanical assembly are going to be first, the method to allow the de-assembly, for example, by using the 3D fasteners, or some methods to create a permanent joints like using the rivets. But in all the cases, the parts are not one part. They can be de-assembled if you break the rivets. The mechanical assembly is the ease of the assembly, which can be accomplished within the relative ease by the unskilled workers. We can so we're going to have minimum special tooling required, and relatively is going to be done in short time. And also we have to ensure the ease of the de-assembly process. So by at least the methods that permit the de-assembly process, and some de-assembly are going to be required for most of the products to perform the maintenance and the repair. You don't want to weld the parts of the engine car together because you have to de-assemble it later. So this is the first method. We can have the 3D fasteners. We can use the screw or bolts and nuts. Mainly for this one, we're going to join the parts. For one of them is going to have the through hole. The other one is going to have the blind hole. The lower part is going to be the threaded one. In the case of the bolts and nuts, we're going to have two through-hole parts, and we're going to have no threaded going to be available, and then we're going to use the bolts and nuts to hold the parts together. So the 3D fasteners is a discrete hardware components that have external or internal thread. Of course, this is the external, and the nuts have the internal thread, and used for the assembly of the parts. Common threaded fasteners are going to be the screw, the bolts, and the nuts. For the screw, it's externally threaded fasteners for the blind holes. The bolts is externally threaded fasteners inserted into the through holes and screwed into a nut on the opposite side. The nut itself is internal threaded fasteners, having the standard threads that are going to be matched for those of the bolts with the same diameter, pitch value, and the thread form. For the rivets, usually it's going to be a permanent types, unthreaded types, unthreaded headed. Pins which use to join the two or more parts by simply passing the pin through the holes and the parts, and then we're going to form the second head on the pin on the opposite side. It's widely used fasteners for achieving the permanent mechanically fastened joints, and the clearance of the holes is very must be close to the diameter of the rivet, so no movement is going to have between the hole and the diameter of the rivet itself. Okay, also we can do the press fitting. For example, if I'm going to fix the ball bearings on the shaft, so I have to press it with some force because the interference is going to be too close, and thus we're going to have the shaft almost permanently fixed inside the hole. The press fitting or the interfacing fit is typical case, which is going to be the straight cylinder pin of a certain diameter is going to be pressed into the hole of slightly smaller diameter. And this can be used for the locating and the locking of the components. And also it's used for the pivot points and for the shear pins. The snap fit, now usually this one is used for the plastic parts, but still it's going to be possible to use for the metal. It's joining of the two parts in which the mating elements are going to be poses a temporary interface during the assembly, but once assembled they are going to be interlocked together. During the assembly, one or both of the parts are going to be elastically deformed. This one is going to be elastically deformed and go back to the original shape to accommodate the temporary interface. We can use the retaining ring. If I'm going to have the groove in the shaft, I can use the retaining ring to stop the material from moving along the shaft. I can use the stitching by using the wires, and I can use the stapling, which is something similar to the stitching, but it's going to be done in one process. So do we have any question about this lecture? Okay, did I upload the lecture notes is available already, right? Yeah. Okay, so once again, I will post you the video for the gear pump, which is going to be started, I think, from this week. And you are going to finish it over 4 weeks sessions before you're going to supply it. If you know where my channel is on YouTube, I think if you search, you can find this video. But anyway, I'm going to send it by email tonight. That's it for tonight. I didn't give you a break because we finished